Hello and welcome to the session on LC oscillation. So in LC oscillation what happens is, say you take a capacitor, charge the capacitor with a battery and take that charged capacitor which has say some charge Q naught in it. Take that capacitor and connect it to an inductor. What happens after this is called as something an LC oscillation. So meaning that the charged capacitor which was there, it stored electrical energy and then the capacitor will get discharged. The energy of the capacitor will get stored, part of the energy will get stored as energy in the inductor, magnetic energy. So magnetic field will start developing in the inductor and energy will keep oscillating between the electric field and magnetic field. So this kind of oscillation is called as an LC oscillation. So I am going to explain that through certain circuit diagrams. So what we have is, you take a charged capacitor which is having a charge of some Q naught, and then you take the charged capacitor and connect it to an inductor. So let's say capacitor has capacitance C, inductor has self-inductance L. And what happens after this connection is what we are going to discuss. So let's start over here. So this is a fully charged capacitor. So there is a switch which is initially kept open, and let's say at t equal to 0 we are going to close the switch. Okay, so when you close the switch, current will start flowing in the network. So charge of the capacitor will reduce from Q naught. It will become some Q, keeps on reducing with time. So after some time the charge on the capacitor has reduced, it has become Q, and there is some current flowing in the network. So this current flowing will give rise to a magnetic field in the inductor. Okay, so a magnetic field gets developed in the inductor, which I am showing like this. So the sense, I am not showing the arrow marks on the magnetic field. In fact, it is going to be completely present inside that inductor over there. So I am not putting the arrows because that depends on whether it is going to go in the clockwise sense or anti-clockwise sense. So you have some magnetic field being developed in that particular inductor, and the charge on the capacitor has been reduced. Now further what will happen, the charge will further reduce and eventually the charge will become 0. Then you will have maximum current in the circuit. Current is I naught. So you will have a greater magnetic field which is going to be there in the inductor. Greater the current, greater the field. So you will have a greater field strength that gets developed in that particular inductor over there. So I have shown it with like 4 loops. So here I am only showing 2 loops, here I am showing like 4 loops. So you have greater magnetic field developed in this particular inductor. So you see that the electrical energy now in the capacitor will be completely 0. All the energy will be as magnetic energy in this particular inductor. And I suppose you know that energy in a capacitor, the electrical energy will be Q square by 2C, and energy in an inductor will be half L I square. So initially what will happen, the charge will keep on reducing. So the energy stored in the capacitor will keep on reducing and it will become 0, and the energy that is in the inductor will keep increasing. Initially there was no energy in the inductor, inductor energy was 0, and then the inductor energy will build up, it will further build up, and from here after this what will happen is, now since the energy, there is some energy built up in the inductor, now that energy will get transferred to the capacitor. So now current will reduce from I naught, the current will reduce, and now this plate will become positively charged. Some plus Q minus Q is there. So now again the capacitor will start getting charged and the energy stored in the inductor will reduce. From I naught the current reduces and further the current will finally vanish. Now in this stage you will have a magnetic field in the inductor. I am showing it with, let's say, only a kind of situation over here, right? So one loop on this side, one loop on this side. So I have shown a similar pattern of 2 loops of magnetic field in the inductor. So here I could have shown electric field. So electric field is there and here electric field is there between the capacitor plates. Now there is no electric field. Now electric field has built up in this capacitor inside, and then further this capacitor will get charged. The field of the inductor, the magnetic field will become 0, current at that instant will become 0, and now the capacitor will be like having its charge Q naught but in the reverse polarity. And so this got fully discharged, and then the inductor had energy. Now that is charging this capacitor and it becomes like plus Q naught minus Q naught. Now the energy in the inductor has fully vanished. So from this polarity you have attained a reverse polarity over here. Now what happens is, again this capacitor is fully charged, and it's like you take this charged capacitor and connect it to an inductor. No current is there in the circuit now, and what will happen now, since this is positive charge, now current will start flowing in this direction. Now current start flowing like this. Now when current builds up, the energy in the inductor, magnetic energy due to magnetic field arising due to current flow, that will start building up again, and now you will have electric field which will be reduced, and from this again the charge is there will further reduce and the charge will become 0 on the capacitor. Now you have maximum current in the circuit and magnetic field will be built up to a stronger extent in this particular case. So you come back to this particular situation. Now the magnetic energy that is there in the inductor, that will start charging the capacitor. Here the charge was 0. Now this current will start reducing. The current which was I naught will reduce, become I. It will charge the capacitor. You will have electric field lines over here, and of course the current has reduced, so lesser strength of the magnetic field in this case. And further the field will reduce, become 0, and the capacitor will be like fully charged. It will become from plus Q, it will become plus Q naught and minus Q naught on the bottom plate. Now you will go back to the original situation. So this will complete like one full cycle, and it will keep on repeating. This cycle will like keep on repeating over and over again. The energy will get transferred from the capacitor to the inductor to the capacitor. You see what has happened over here. So energy has been from this state, in this state, energy has been fully transferred to the inductor. The electrical energy fully got transferred to the inductor over here, and then that energy got fully transferred back to the capacitor. Okay, so you have energy back in the capacitor fully, no energy in the inductor, and then that energy now gets transferred to the inductor again, and here that inductor is having its maximum energy, capacitor has 0 energy, and then the inductor will start charging the capacitor again. You will have energy built up in the capacitor, finally back to the maximum state. So you will come back to this state over here, right? So this will complete like one full cycle for the charge getting fully transferred out of the capacitor, and it becomes 0, and then it becomes Q naught over here again in the reverse polarity, then again it becomes 0, and then comes back to the original state. So that completes one full cycle. Okay, so this was one part of it. Next we will see how to go about writing mathematical equations, how this charge on the capacitor will vary with time, how the current in the circuit will vary with time, and we will try to plot graphs for the charge variation in the capacitor and current variation in the network. So that will be an interesting graph. So I'll just erase the board and be right back. Alright, so now let's try to formulate equations. So what I have done is, assuming that at t equal to 0, charge on the capacitor was Q naught, you close the switch. So capacitor started getting discharged, and I have drawn the circuit after some time equal to t, where charge on the capacitor is Q and some current is flowing in the network. Now what we'll do is note that this current is flowing out of the positive plate of the capacitor. So I flowing out of the positive plate of the capacitor, this I will be equal to minus of dq by dt. So if current enters the positive plate for the capacitor, we will write I equal to plus dq by dt, whereas if current flows out of the positive plate of the capacitor, we will be writing I equal to minus dq by dt. And also the potential difference across the capacitor and potential difference across the inductor, that is the difference in potential of these 2 points. So I'll write it A and B. Here I'll write it as like say P and Q. So potential difference of the point A and B is going to be Q by C, and potential difference of the points P and Q. Note that current is entering at P and leaving at Q. So potential difference of the points P and Q will be equal to L di by dt. Potential of the point where the current enters minus potential of the point where current leaves in an inductor. That difference in potential is going to be L di by dt, and VA minus VB will be Q by C, and VA minus VB should be same as VP minus VQ. So we will have this equation, potential difference across the capacitor Q by C will be equal to L di by dt, but I itself is minus dq by dt, so we will have di by dt equal to minus of, differentiate both sides, minus of d square q by dt square. So in place of di by dt, we will substitute minus d square q by dt square. We will have the equation q by c equal to L times di by dt is minus of d square q by dt square. So what we will do is we will rearrange this, and write it in the form d square q divided by dt square equal to minus 1 by LC times q. So you note that this is of the form, this equation, this differential equation is of the form the simple harmonic oscillation. If you remember, d square x by dt square equal to some minus constant times, that constant is omega square x. So it is precisely of that form where x is nothing but q and time, in place of time we have t only. So in place of x we are having charge. So this term over here 1 by LC, that will be represented with omega square, and we can write this as d square q by dt square equal to minus of omega square q, where omega square is 1 by LC, which is the angular frequency of this particular oscillation. See, why we call it oscillation is because energy is like oscillating between the electric field of the capacitor and magnetic field of the inductor. So that oscillation continuously takes place, and that oscillation is happening with an angular frequency of 1 by LC, and also it is a simple harmonic oscillation because of this equation where you have d square q by dt square is proportional to minus q, just like this, where d square x by dt square is proportional to minus x, a simple harmonic oscillation. D square q by dt square is proportional to minus q, it will oscillate simple harmonically. What oscillates simple harmonically? Meaning that the charge on this particular capacitor will be varying sinusoidally. So you take this equation, and solution for this equation, you can write it just like how you write the solution for a simple harmonic equation. So for a simple harmonic equation over here, with maximum x value being amplitude, you write it as x equal to a sine of omega t plus phi. Right, so phi is the initial phase angle of oscillation. Similarly, we will do it over here also. The maximum value of q is going to be q naught. So we will put q equal to, solution for this equation, q equal to the maximum value of charge times sine of omega t plus phi, where our omega will be equal to 1 by root of LC. Alright, so we have how q varies with time. So we have to get this value phi also, the initial phase angle. To get the initial phase angle, we will make use of this condition. At t equal to 0, charge on the capacitor was q naught. So you put t equal to 0, q should be equal to q naught. So sine phi should be 1. So if sine phi is 1, you will get what should be the initial phase angle. So initial phase angle for the charge, that should be equal to pi by 2, because at t equal to 0, q should be equal to q naught. So we make that substitution. So once we make the substitution, we will have q naught equal to, I am putting here q equal to q naught at t equal to 0. So q naught equal to q naught sine phi, omega into 0 plus phi. So we will get, from this relationship you will have sine phi equal to 1. So what we are doing is we are getting the initial phase angle. So phi will be equal to pi by 2. So how will our charge vary with time? Q equal to q naught sine of omega t plus pi by 2, or you can also write it as q equal to q naught cos of omega t. So that will be the variation of charge with time. So it will be of this form, q equal to q naught sine of omega t plus pi by 2 just becomes cos omega t, and I is dq by dt with a minus sign, of course. So differentiate this with respect to time and put a minus sign, you will get current variation. So this current variation will be equal to, differentiation of cos will become minus sign, already we have a minus, so that minus and minus will get cancelled out. We will have q naught omega sine of omega t. Right? So this will be the current variation in that particular network. So you see that the peak value of charge, maximum value of q will be q naught, whereas maximum value of current, this one I naught, the maximum value will become q naught times omega, where omega is 1 by root LC. The angular frequency of oscillation of the LC circuit. Okay, so these are the mathematical formulations. Now let's also discuss something about the energy which keeps switching over between the capacitor and the inductor. Okay, so that's another part of discussion, how the energy keeps shifting and what will be the total energy of this particular system. So I'll erase the board and be right back. Alright, so just now have a look at this. At t equal to 0, this capacitor had charge q naught, and we have connected this capacitor to the inductor and closed the switch. So this is at t equal to 0, where the total energy of this system is only electrical in nature. There is no current initially, so there is no energy stored in the inductor. So only energy is stored in the capacitor, and that energy is going to be Q square by 2C, where the charge is Q naught. So Q naught square by 2C is the total energy of this particular system. Now after time t, there is some charge Q on the capacitor and some current I is flowing in the network, and Q variation with time we have already obtained, and I variation with time we have already obtained. So this is Q variation with time, and this is I variation with time. So you see that Q varies as a cos function and I varies as a sine function. Now at this instant, let's find out what is the total energy stored in this particular system. So now capacitor also has some energy, inductor also has some energy, because Q can be non-zero, I can also be non-zero at some generic time t. So now let's find out. The total energy will be sum of energy in the capacitor and the inductor. So now the total energy will be equal to Q square, the charge on the capacitor, Q square by 2C plus half L I square. Energy in the inductor is half L I square. So let's sum this up. So Q is nothing but Q naught cos omega t. So Q naught cos omega t the whole square divided by 2C plus half L I square is going to become Q naught square omega square sine omega t whole square. Okay, now we know that omega is 1 by root of LC. So omega square will be equal to 1 by LC. So you put omega square as 1 by LC and you simplify this expression, you will precisely find that this total energy will be equal to Q naught square by 2C, which means that it is independent of time. So that's the most beautiful thing about this. So the total energy that is stored, that does not change with time. It is always, see, initially you had total energy of Q naught square by 2C, and at any generic time you still have the same energy of Q naught square by 2C in the total system. So energy in the capacitor will get reduced, and accordingly the energy in the inductor, the magnetic energy in the inductor will increase. Okay, so total energy of this is going to be a constant. So what they can sometimes do is that there can be some problems. What they'll do, they will give you the capacitance value. So I'm talking about a problem. Okay, so after making note of these things, you can just try to make a note of this problem. I'm not going to solve it fully, but I'm telling you how to make use of the concept that we just discussed to find out certain things. So what they can give you is the capacitance value can be given, inductance value can be given, and also they will say that this capacitor is initially charged to a particular value, which means Q naught value is also given. And what they can ask is, when the charge on the capacitor has become a particular value, what will be the current in the circuit? So what you can do, you can say that at the total energy at any instant will be same as the initial total energy. So you will just take the total energy at any instant, which will be Q square by 2C plus half Li square, and equate it with Q naught square by 2C. So you know Q naught value, you know capacitance, you know inductance, and what they are saying is, when Q, the small q has attained a particular value, how much current is there? So small q is also given, you need to find out I. So you will equate Q square by 2C plus half Li square with the initial energy, where you know Q naught, you know L value, you know C value, and Q value also they are giving Q value and asking you to find out when Q on the capacitor is a particular value, how much is the current. So you can equate the energies and find out the current value. Okay, and also you can look at this graph, how Q and I varies with time. So if you just try to plot that particular graph, Q variation and I variation with time. So I'll just plot Q variation first, how charge on the capacitor varies with time. So at t equal to 0, you have charge Q naught initially, and it is a sine function. So it will vary sinusoidally like this. I'm just drawing it for one full cycle when the charge is again become Q naught over here. That is one, that completes one full cycle. So what happens is, charge is initially Q naught. After 1/4 of the cycle, it becomes 0. Then wait for one more 1/4 of the cycle. So the charge becomes like minus Q naught, meaning that the polarity reverses. Q becomes minus Q naught. So this is like Q versus time. So initially Q is Q naught, and after half a cycle Q will become minus Q naught, meaning this plate will become minus Q naught, this will become plus Q naught, and then the charge will increase, become 0, and then it will finally become Q naught again. So that will complete one full cycle, and the cycle will keep on repeating. And the time taken for completion of one full cycle, that is nothing but time period. So from this point O to the point over here, that time taken, which is nothing but time period, one full cycle. time taken for one full cycle, that will be nothing but 2 pi by omega, and omega is nothing but 1 by root LC. So you can substitute omega equal to 1 by root LC, and you will write that time period for the cycle will be 2 pi root of LC. So that is the time taken for one full cycle to get over. So that is Q variation with time. Likewise, you can even get I variation with time. So you can draw a graph using this. Q naught omega is nothing but the peak value I naught, and it's a sign variation. So at t equal to 0, initially the current was 0. So you will plot a sine graph like this, right? Where initially at t equal to 0, you had 0 current in the circuit, and then it becomes I naught, the current reduces, becomes 0, and then the current direction reverses. So you can just look at those initial set of LC oscillations which we drew, right? So it starts at some location, comes back, and then it attains the full cycle is over. And so the current reverses direction, it will become minus I naught over here, or I peak or I naught in the reverse direction. So that is what we are saying here. It is minus I naught, and then it becomes finally 0. So this is I versus time. So this also will be over in a time of 2 pi. This one full cycle will be over in a time of 2 pi root of LC. Right, so when charge is varying like this, your current would be varying in this particular manner. Okay, so charge variation versus time, I variation versus time as a graph, and total energy of the LC system remaining constant. See, this is an ideal case that we are discussing, where there is no resistor involved in this, so there is no energy dissipation. In fact, we are also assuming that the connecting wire has no resistance. In practice, that is not going to be the case, but we are just assuming an idealistic situation where connecting wires are also ideal and there is no resistance involved at all. And when there is no resistance involved at all, so Q and C, the energy will keep on oscillating between the inductor and the capacitor. Alright, so this is what is about an LC oscillation. Right, all the very best. See you in another video. Bye.